This is the sharpest nose cone I've ever made. It's a conical 5-degree half-angle constructed from turned and polished aluminum on top of fiberglass biaxial sleeves formed around a mandrel. The enormous cutout in the side will let me deploy a payload at apogee. This device is a camera that looks back at the rocket to capture the drogue parachute deployment in slow motion. But this cutout has downsides. It's an aerodynamic mess and a structural weak point, so when the nose cone hits Mach 2, I need it to not collapse. I have an idea for how to fix this, but let's start by getting the fiberglass into the right shape. I started by printing the inner mold in 4 pieces. The base is flared because a flared base is always important. It helps the mold stand upright and it makes sure that it doesn't get stuck. The mold includes a long length of upper section which couples with the guidance package and houses the camera pod. After the 5-degree taper on top, the nose is largely empty except for a plug which keeps the aluminum nose tip attached. To connect the mold sections, I used CA with a little bit of accelerant. Centering these parts with as little lip as possible is important, as the mold won't come out cleanly if the ridges get stuck. To make the whole mold stronger so I can pull it out, I also ran a 1/4-20 threaded rod up through the center. The tip isn't rounded here like previous nose cones because for this one I decided not to use condoms. If you're new here, I like to use condoms as mold release devices for nose cones, and specifically I've been using these Titan XXL condoms, but I had a lot of trouble getting these to work on my meat rocket. I should be more specific. I had trouble getting these to not break on the inner diameter mold for the nose cone for my rocket which reached Mach 3 to cook a piece of Wagyu beef. Side note, I bought these from a website called Lucky Bloke, who are very sad to see that I'm not ordering more. I don't really have the heart to tell them that if I'm not making nose cones, there's nothing else I can use this for. This nose cone is much longer than the previous one, so instead of struggling with the condoms, I gave the whole mold a generous coating of superlube to fill the gaps between the ridge layers. Then I brought it outside to give it a coat of E236 mold release for extra protection. This is the same mold release approach I used for the first nose cone I made for the meat rocket, and it didn't work great. I don't think it moved. Uh-oh. I removed all of the infill. I should have used a condom. The key finding with that nose cone is that while Superlube and E236 don't do great on their own, applying just a bit of heat softens the PLA enough to peel it out, and that's my plan here. Like my previous nose cones, I'm using Solar Composites biaxial weave for this layup. I measured the length to use as a template, then cut a total of 9 layers out for the layup. I don't have hard numbers on this, but 9 is a lot more than I should need for a 4-inch nose cone going Mach 2. There's a huge cutout in the side of this nose cone, which means we're losing a lot of strength, so that's why I'm going so overkill with the 9 layers of fiberglass. For epoxy, I'm using Fiberglass System 2000 with the 2060 hardener, so I've got about an hour of time to work with it before it starts hardening. I was real generous with the epoxy pour here, and I should have used 2 smaller cups because filling it to this size made mixing really difficult. So eventually, I just started pouring the epoxy between one cup to the next. This seemed to work well enough, so I started the layup. I worked on this 1 layer at a time. I slid the sleeve onto the mold, grabbed some epoxy with my hand, then massaged it in until the fiberglass was soaked. I repeated the process for each sleeve and kept the epoxy application pretty generous, meaning that I'm probably using too much here. A good layup has just enough epoxy, but having too little is a lot worse than having too much. I was so generous that near the last few layers I had to mix a second batch of epoxy since I had run out. Lots of the first batch ended up dripped on the mat or pooled at the bottom, so this process is just very messy. I spent quite a bit of time near the end just massaging the whole layup to make sure we didn't have any bubbles between the layers, and once it looked good, I let it sit for a few days to cure. Once cured, my plan was to use space heaters so that I could soften up the PLA, peel it off, and pull it out. And this only kind of worked. I should also say I pulled really hard on this thing to see if I could get it out just naturally, and that did not work at all. I tossed it in front of a space heater to delaminate 1 layer at a time, which sort of worked, but I quickly realized that the way I had printed this mold was working against me. I had printed this mold with infill, and next time I'd probably go with a vase mode print instead of having any infill. The infill here does a great job fighting the ability for the mold to collapse, which would allow it to peel away from the inner wall. Any infill, even if it's not very dense, is pressing that mold against the fiberglass. And in hindsight, this was the case with that first nose cone for the meat rocket as well. It wasn't until I had percussively removed the infill that the mold was able to be peeled out. The PLA did soften like I intended, but it was clear that I was in trouble and this wasn't coming out easily. Now, this thing doesn't really fit in my oven, but it was clear that the space heater wasn't going to cut it, so I set my oven to preheat to 230 degrees Fahrenheit. Now is probably a good time to explain why this is risky. Fiberglass composites have thermal limits. The fiberglass itself can chill at really hot temperatures. I mean, it's literally glass. The epoxy can't. The datasheet for System 2000 says that under the right conditions, this can work up to and beyond 200 degrees Fahrenheit, and its successor, the 2001 series, can go up to 240. Now, PLA should have a glass transition temperature of around 140 Fahrenheit, but it's not going to actually melt until 300, so we can't just melt it out without damaging the epoxy. This thing doesn't really fit in my oven, so I chopped off a bit of the bottom and covered it in aluminum foil just in case something did melt out, whether the PLA or the mold release. Then I tossed all of that in my oven, closed it as much as I could, and covered the top in aluminum foil to try and preserve the heat in there. Starting at 230F in the oven didn't do much, and when I pulled it out, I could only demold some parts. Most of the print was still stuck in there real good, so I figured I had to go hotter. At the risk of damaging the epoxy, I pushed the temp up to 340F and let it sit for longer. This worked a lot better, and I was able to immediately remove the bottom of the mold as well as the two midsections by the 1/4-20 rod.
I got it. Oh no! Okay, so there's still some up in the tip.
Before dealing with the last upper section, I lopped off more of the bottom and top of the nose cone since I was sick of getting poked by the fiberglass shards. On the bottom section, you can see the epoxy has darkened a bit here, which means we probably did damage it a bit. It doesn't look too bad. My Vibometer says it's probably fine, so we're gonna assume that we have enough margin in here that a slightly cooked epoxy is gonna be okay. For this last mold section, I tossed it in front of a space heater to soften it up, then peeled off the internal edges with the file and hammered it out. This approach worked, but like, barely.
There it is. Nice.
I wasn't planning on this mold being reusable, and my gosh, it certainly isn't, but once again, I find myself thinking that this is not gonna work for the 8-inch space shot. We're never gonna be able to make nose cones if this is how it goes every time. My thought for next time is I might try latex balloons stretched over the mold. They'll be able to stretch further than the condoms without breaking, and they'll smooth out those ridge lines. And I just picked up some Teflon coating spray that I think might help too, but if you have ideas for what to do differently next time, I am all ears, because this is clearly not working. So this nose cone still needs some work. The outside is pretty rough right now, but there's also a problem with the inside. I copied the exact dimensions from the inner mold of the Meat Rocket nose cone, which used 3 or 4 XXL condoms as a mold release. So without the thickness of those extra condoms on here, this doesn't fit on the guidance package anymore. The guidance package is over here, but it's got a bunch of stuff hanging out of it. So I'll use this coupler tube, which is the same diameter. This does not slide on top of the coupler tube. The inner diameter of the nose cone is too small, and I don't want to change the dimensions of the coupler tube because it's the existing guidance package, so we have to widen out the inner diameter of this. I don't know exactly how I'm gonna do that yet, but I'm gonna trust Future Joe to figure it out. Future Joe is great, by the way. He picks up all the slack from the bad decisions that present Joe makes. Anyway, our first step here is I want to smooth out the outside of this nose cone. Actually, Past Joe lied here. The actual first step is getting the top and bottom of the nose cone square. I set up my shop vac with a HEPA filter, then attached it with a rubber band to a mic stand to catch any of the little particulates that fly off. Then I grabbed a cutoff tool and put the nose cone on the lathe. I removed the jaws from the chuck and put the tip of the nose cone into the chuck hole, then secured the other end with a bull nose live center. I cut off enough of the base to get the edges squared, then I sanded down the frays on those edges with a bit of sandpaper. Then I did the same thing for the nose tip. This time I mounted the base flat against the chuck face, tightening it with the jaws since we know that that surface is now square, and then I put the tip in a smaller live center on the other end. And with these two edges cut, I got to work sanding the edges clean. Sanding takes a long time. It's my least favorite part about composites. It's all sanding. So while I'm working on this, let's talk about how we're gonna reinforce that huge cutout in the side of the nose. I got these aero covers machined by PCBWay, and they're made out of PEEK plastic, which we'll talk about in a sec. These little guys are gonna increase the stiffness around the area of the cutout. I got several of these made just in case I messed a few up, and because of how cheap the process was. I'm gonna cover these in paint eventually, but the machining finish on these is excellent. PCBWay made several parts on this project. In the last video, I showed you how they made that acrylic door, which we're no longer using, but came out great. And for their CNC services, they'll do all sorts of materials: aluminum, steel, titanium, copper. They'll also do composites like carbon fiber and FR4, which is crazy. It's very hard to find a machine shop that will machine composites. And maybe you've got a part that could benefit from 3D printing, whether plastic or metal, they can do it. Bent sheet metal, injection molding, vacuum casting, all of this in addition to PCB fabrication and assembly. These guys do it all. Sometimes you don't have the time, expertise, or tooling to make your own parts, and that's why services like this are so helpful. And you can get a really quick quote using their online quoting tool. I've really enjoyed working with PCBWay on stuff like this, and if you want to give them a shot, there is a link in the description down below that's going to get you a sweet deal. Thanks so much to PCBWay for sponsoring this video. I really recommend you check them out. And now that we're done with sanding, let's talk about the outer surface of this nose cone. My intention here is to use a fairing compound to smooth out the bumps in this surface, but it's very rough right now, so to start, a little bit of sanding should go a long way. I'm not trying to get an ultra smooth surface, I'm just trying to reduce the amount of filler we need to use to smooth this out. I'm doing my best with dust control here, but for these first few passes, I forgot to add some paper towels over the ways. Composites on a lathe are just no fun. After sanding the conical section, my goal was to use one of the lathe tools to run straight down the side of the nose to smooth that out rather than sandpaper. But as you can see, this thing is a little lopsided, and I'd obviously be cutting more off one side than the other, so I had to use sandpaper. I guess I'm not surprised this came out a little bent. They're 3D printed molds and it's a rough layup process, but I'm not worried about this causing problems in flight. I just should have known it wasn't going to be machinable. With the sanding done, you can see the surface is much smoother, but it still has all these pock marks. This is the point where I stopped on the Meat Rocket nose cone, and even in the finished product, you can see the results. The Meat Rocket nose cone has all these little pock marks, which are probably increasing our parasitic drag as we go through the air, and even if they're doing nothing aerodynamically, I just don't like the way they look, so we can fix that with a little bit of fairing compound. I'm using Bondo here, which I have never used. You are watching me use it for the first time, so please be nice to a newbie in the comments. This stuff hardens really fast when you mix in the curative, so I panicked about halfway through and started adding way too much. I knew that I'd be able to sand it off. I mean, this stuff being sandable is literally the whole point, but my God, why did I do this? It hardened fast enough that halfway through this application process, I had to stop, wait a little bit, and then apply another newly mixed coat. Like, I literally did not have time to coat the whole thing in Bondo because it cured so fast. Here's what I've learned about Bondo so far. First, I think I used too much. In hindsight, it's very clear I didn't need to add this much. I just really wanted to make sure it was coated well. One thing I love is how fast this stuff hardens. It took 2 coats to get this whole thing, and I think if I were a little more patient and did it in 3 or 4 coats, I wouldn't have had to use so much. It should sand really easily, so it should all come off easily, especially on the lathe. But for future nose cones, I think I can do it a little more patiently with less Bondo and less sanding afterward. It also smells awful. Like, I can't even describe how bad it is.
Man, that cannot be good. Okay, that cannot be good. Whew, that is gross, dude.
I don't think you really need to wear a respirator when you're working with Bondo. No, that is wrong. You do need a respirator. Hi, it's me. In the future, you do need a respirator. It needs to have organic cartridges. Ideally, it's also N95, but the organic vapors are what you're worried about. These things do nothing for organic vapors. You want this, not this. This is a great example of why you shouldn't trust everything I say or that anyone says. Everyone is wrong sometimes, and if it involves your personal health or safety, you should always double check it by at least Googling it, which I clearly failed to do here. I also thought of an idea in the meantime to widen out the inside of the nose cone so it'll fit on that coupler. I'm pretty sure it will work, but before I tell you, let's get all this Bondo off. This followed the same process as the initial sanding, but with a lot more dust, and this time I actually did cover the ways of the lathe. The Bondo isn't perfect, and there are a few high and low spots with this stuff, but it made an enormous difference. Obviously I missed a few spots, but I'd say 95% of the little pock marks are gone, and this nose cone is looking real smooth to me. As far as techniques for making future rockets, this one was absolutely worth the time and effort. So now that the outer surface is smooth, let's refocus on widening that inner diameter. So I had an idea. In an internal combustion engine, the fit between the piston head and the cylinder needs to be very tight so that it's a good seal. And to get that tight fit, you need really good machining. But we're talking about single thousandths of an inch in terms of tolerance for that seal. So how do you hone in on that dimension for the cylinder? The answer is this device. You can use this to hone in on the inner diameter of a cylinder. So we call it a cylinder hone. I love when things are named so cleanly. This thing hones in on cylinders, so it's called a cylinder hone. Like, why do they call it Amtrak? It's because you am on the track. Each one of these arms is spring-loaded, so it's always got a little bit of pressure on it. You can adjust that pressure with this spring and knob down here, and on the very end are these pivoting blocks with a little bit of grinding material. If I put this thing on a drill and spin it a bunch, it's gonna end up grinding the inner diameter of whatever it's inside. So we're gonna use this inside of the nose cone to gently widen out that inner diameter and make sure the fit between the nose cone and the guidance package is tight. Using the cylinder hone, I started by trying to use the grinding blocks themselves. These are usually made of a few different materials, like silicon carbide, aluminum oxide, or sometimes nicer abrasives like diamond or cubic boron nitride, and I wrote this part into the script so that I got to say a bunch of fancy words. Unfortunately, those fancy words don't do anything to the fiberglass because I still had a thin layer of superlube coating the inner diameter, which gummed up the abrasive. I tried scraping this off a few times, but eventually decided to throw more abrasion at the problem. I hot glued 240 grit sandpaper to each block and gave that a shot in the nose cone. This was better, and I could definitely see bits of fiberglass being sanded away, but the sandpaper was still getting gummed up. I tried cleaning this with lots of IPA, but it didn't help much, so I went lower on the grit by switching to 120. This did more, and I could tell we were moving in the right direction, but I still wasn't happy with the progress, so finally I went all the way down to 60 grit sandpaper. As I went, I kept checking the fit with a spare fiberglass coupling tube, honing, then checking, then honing again, then checking again. I must have sanded off almost an entire layer of fiberglass because by the time I was done, I realized I had sanded my way into a bubble. This is a void where the epoxy hasn't seeped into the fiberglass weave and now it's just kinda loose fiberglass. It looks like there's only one layer where the epoxy isn't present, and I can spot one or two other spots in the nose cone where this is the case. And it feels like the darkened epoxy for me. I think we have enough margin to tolerate some problems like this, but would love to not do this next time. The last big step for the fiberglass is to create the holes that mount the camera deployer and that massive cutout for the camera to shoot through. To get all those in the right place, I designed and 3D printed a drill jig, then hot glued it in place around the nose cone to keep it really secure. Then, I used a pencil to draw the boundaries on where each cutout needed to happen, and started drilling holes to mount the deployer. I also drilled 2 access holes which I'll use to turn on the power switches for the 2 flight computers that are mounted on the deployer. To remove the drill jig, I released all the hot glue with IPA, which let it slide right off. Then I got to work with a Dremel and a cutoff wheel to create the door hole. I cut this hole out in 2 pieces, then spent a lot of time sanding the corners to round them off and reduce stress concentrations. Then I flipped to the other side to drill a hole where the camera pod's lens would be during flight. It's not a primary goal for this thing to capture footage during ascent, but if the camera is rolling, we might as well add another hole to get a cool shot. These cutouts weren't perfect, and especially with the large cutout, I left a few nicks in the fiberglass, but that's why we're reinforcing this area. We're gonna do that reinforcement using this plastic aero cover made of PEEK, P-E-E-K, which stands for polyether ether ketone. I don't know why they put ether in there twice, it's probably just inflation. But it's a high-performance polymer that is RF transparent, and that's important for all of the sensitive computers inside. This part was machined by PCBWay as part of the sponsorship I mentioned earlier, and we're going to use it to make the outer surface much more smooth. Using a dummy pod, I made sure there was enough clearance for it to deploy.
This is so cool.
Then I roughed up the surfaces and mixed up a batch of epoxy with some ceramic powder as a filler to make sanding easier. I drew an outline of where the peak aero cover needed to sit, and to protect the inside from stray drops of epoxy, I used blue tape. Then I carefully covered the area in epoxy and attached the aero cover. The tolerance here is very tight though, so I worked with the cure time of the epoxy to gently make sure it was in the right place. I let the epoxy sit for about an hour, and by that point it had started to harden, but it could still be nudged around like a soft putty. So I removed the blue tape, cleaned up the surrounding area, then added the deployer and a dummy camera pod. I used this with some popsicle sticks to center the aero cover around where the camera pod will actually sit, and I left it overnight to cure fully. In the morning, I removed the camera pod, which you can only do by shooting it out. Love that. Then I got to work sanding the area to make it nice and smooth. The peak and epoxy with filler both sanded beautifully, and it ended up being a really nice smooth surface. At this point, all of the sanding, drill holes, cutouts, etc. are done, so it's time to give this thing a coat of white paint. I'm using a white gloss enamel for this, and as a general rule, this stuff goes on a lot easier when it's warm rather than cold, so I soaked it in hot water for about 30 minutes before spraying it. It's not a perfect paint job. You can tell that there's some overspray and the surface isn't totally perfect, but if you're standing far enough back, I think it looks great. This is probably like a 5 or 10 foot paint job. While this thing is drying, you have probably noticed by now that we're missing the most important part of the nose cone, the pointy bit. This part I'm making out of 6061 aluminum round bar stock. The nice thing about cutting out of 2-inch bar stock is that it can fit through the spindle bore, so I don't have to cut the stock to size on the horizontal bandsaw first. After removing everything that would let the lathe perform cosmetic surgery on me, I got to work at the base of the tip. I spot drilled, regular drilled, then tapped a 1/4-20 hole in the center, which I'll use to connect this tip to the nose cone. Then I turned that inner lip down to size and double-checked the fit with the top of the fiberglass section. When that looked good, I gave it a cheeky chamfer and removed the stock. We don't need all of this for the tip, so I measured a little more than I needed and lopped off the rest with the bandsaw. Then I mounted the resulting part back on the lathe, offset from the chuck with gauge blocks, so I can turn the taper all the way to the end of the part without colliding with the jaws. Next, I set the taper on the compound to 5 degrees and started turning from one end, but then decided to change my approach and focused on turning the whole thing to the maximum outer diameter. The rest of the process was similar to this. I'd start really conservative by machining the taper down at the tip of the nose, then I'd realize I was barely making a dent and cut down the length. Eventually, the strategy I liked most was cutting the taper mostly to where it needed to go, with just a few reliefs along the way in case I overcut anything. What's really tricky about this is that my compound slide isn't long enough to do the entire taper at once, so I have to cut it up in sections and then blend those two sections together really carefully so that we don't leave bumps. Eventually, I cut the final dimensional pass from the base to the tip of the nose cone, and on this cut, I managed to lop off the forward end. Once this fell off and we didn't have the support of the live center, I switched over to sanding. I started at 320 grit, then moved up to 600, 1000, 2000, then moved to a polishing compound. I massaged that around for a minute or two, then removed it to reveal an extremely shiny, extremely pointy nose tip. And by the way, there is a good reason that the nose tip is this pointy. It's just that the good reason is that I think it looks cool. The downside, of course, is that it will go right through your hand if you're not careful. Ask me how I know. I'm mostly kidding. I have poked my hand on it a few times, and it hurts. I can't always be careful, so I designed this 3D printed nose tip protector that prints in 2 halves.
This is ridiculous. Why did I make it this big?
Especially during transportation and storage, this tip is a legitimate threat. I swear that when I made this in CAD, it looked so much more reasonable. Like, you can be sure that you aren't gonna get poked, but man, this thing looks so goofy. To attach the tip to the nose cone, I 3D printed a slug of PLA with a 5-degree taper to match the inner diameter of the fiberglass. Then used a 1/4-20 rod with a nut on the end and a ratchet wrench with like 4 extenders to tighten it down. The last step here is drilling a few holes through the nose cone into the guidance package to mount it rigidly on top. In the meat rocket, we used this upper section to store the main parachute, but with this rocket, we're going drogue chute only, so this is fixed in place. Without spoiling the flight, I can tell you that this Nosecone held up great at Mach 2. The 9 layers of fiberglass were plenty to survive well past the speed of sound, even with that huge cutout in the side. And of course, to get it going that fast, I needed a powerful rocket motor. I'm thinking that since I've got a space to make propellant and a formula that works, I should just make my own motor for this. So that's what we're doing in the next video. If you can't wait till then and you just want to see the design, mixing, casting, and test firing for this motor, that is live on the BPS Patreon right now. I publish update videos every 2 weeks about what I'm working on in real time, and that is how this project is funded. I'm so grateful to the folks who choose to support over there, and I'm grateful to you for watching. My name's Joey B. I'll be back with another video real soon. May your skies be blue and your winds be low. Goodbye.